Welcome to this explainer. So, you're diving into the world of data science, machine learning, or AI. That's awesome. But there is one absolute, non-negotiable foundation you have to lay down before you can build anything else, and that foundation is NumPy. Today, we're going to take you from a complete beginner to confidently understanding the absolute backbone of Python's numerical computing. Okay, let's just dive right into it.
To make sure we conquer this material efficiently, we have a quick roadmap. First, we'll meet your new data superpower. Second, we'll go through setup and creating arrays. Third, properties, slicing, and indexing. Fourth, mathematical operations and randomness. And finally, real-world applications and your next steps.
All right, starting right off with Section 1, meet your new data superpower.
So, what exactly is NumPy? Well, it literally stands for Numerical Python. Simply put, it's a ridiculously powerful library designed specifically for numerical computing. Literally every single Python programmer working with data needs to learn this tool. Why? Because it provides these incredibly fast, memory-efficient, multi-dimensional arrays, plus an entire arsenal of high-level mathematical functions to actually operate on those arrays. It is the core engine under the hood of almost every major data tool you'll use in Python.
Now, you might be wondering, hey, don't we already have lists in Python? Why do I even need this? It's a fair question. While standard Python lists are incredibly flexible, they actually become really slow and super memory heavy when you start dealing with massive amounts of data. NumPy arrays, on the other hand, are highly optimized. They're fast, they're memory efficient, and they handle complex, multidimensional data with absolute ease. When you're processing millions of data points, NumPy is the exact thing that keeps your computer from just totally freezing up.
Moving right along to Section 2, Setup and Creating Arrays.
Let's get our hands dirty right away. If you're coding along with me, I highly encourage you to hit pause on this explainer right now and type these 3 exact commands into your terminal or your notebook. First up, install the library by typing pip install numpy. Second, bring it into your project with import numpy as np. That np part, that's the universal industry standard alias. Literally everyone uses it, so you definitely should too. Finally, just verify your installation by printing the version using print np.__version__.
Awesome. Once you've got it imported, creating your very first array is incredibly straightforward. Here's a one-dimensional array. You just call np.array and pass in a standard Python list, like 10, 20, 30, 40. I want you to think of a 1D array as just a simple, flat line of data. It's essentially just a single row of numbers.
But let's be real. Data is almost never just a flat line. Let's build out the scaffold here by adding a bit of complexity. Here is a 2-dimensional array. Notice those double brackets. We're passing a list of lists. You can map this concept perfectly to a flat grid, a spreadsheet, or a math matrix. It has rows, and it has columns.
And of course, we can take it even further into 3-dimensional arrays. Now we're looking at 3 sets of brackets. If a 1D array is a line and a 2D array is a flat grid, I want you to imagine a 3D array as a Rubik's Cube. It has width, height, and depth. Look, it might look like an abstract, confusing jumble of brackets at first glance, but just remember, each extra bracket is literally just adding another dimension, another layer to your data cube.
Okay, on to Section 3, Properties, Slicing, and Indexing. Now, these commands right here aren't just syntax. They are direct commands asking NumPy to hand over the structural blueprint of your data. Think of it like X-ray vision. If you have a mystery array, you can use .shape to see its exact layout, like exactly how many rows and columns it has. Use .ndim to ask how many dimensions it has. Is it .flatline, a grid, or a cube? Use .dtype to figure out what type of data is actually inside, like integers or decimals. And finally, use .size to find out exactly how many individual elements are packed inside that entire array.
So, once you know what your data looks like, you're going to want to grab specific pieces of it. For a 1D array, indexing is exactly like standard Python. R0 grabs the very first element, because remember, we always start counting at 0 in Python. R-1 is a fantastic little shortcut to grab the very last element. And R1 to 4 slices the array, pulling out everything from index 1 up to, but importantly not including, index 4. Hey, if you have your notebook opened, pause this right now and try grabbing the first and last elements of that array you created a minute ago.
Now, for 2D arrays, things get a little more interesting, but it remains super logical. We just separate rows and columns with a comma. So matrix 0, 1, translated into plain English, simply means, hey, go to row 0 and grab what's in column 1. Simple, right? But what if you want an entire column? You just use a colon. The command matrix :1 tells NumPy, give me absolutely all the rows, but only for column 1. The colon literally translates to everything in this dimension.
Next up, Section 4, Mathematical Operations and Randomness. This is where it gets really fun. Before you even do math, sometimes you just need to quickly generate placeholder arrays, and NumPy has some incredible shortcuts for this. Need a 3x3 grid of pure zeros to start tracking some metrics? Boom, just use np.zeros33. Need ones? np.ones 24. What if you want numbers 1 through 10? Use np.arange 111. Or maybe you need exactly 5 perfectly evenly spaced numbers between 0 and 100. That is exactly what np.linspace 0105 does. And np.i4 instantly generates a classic mathematical identity matrix. These little commands will save you from manually typing out hundreds of brackets and numbers by hand.
Okay, so here's the crucial point. This is the real game changer. What happens when we actually do math on these arrays? NumPy uses this magic concept called vectorization. In standard Python, if you wanted to add 10 to a huge list of numbers, you'd have to write this slow, line-by-line for loop to update every single number one at a time. Gross, right? With NumPy, you literally just type r plus 10. That's it. It instantly adds 10 to every single element in the array simultaneously behind the scenes. You can multiply arrays, add arrays together, or instantly find the square root, the sum, the mean, or the maximum values. Absolutely no loops required. It is brutally fast and gives you beautifully clean code.
Another totally massive feature is generating randomness. If you're doing machine learning simulations or just generating dummy data to practice on, you need random numbers constantly. np.random.ran5 will instantly hand you 5 completely random decimal numbers. Or if you need whole numbers instead, np.random.randint 110 will immediately generate 10 random integers between 1 and 100. It's really that simple, and it's built right in.
Finally, let's bring it all home with Section 5, Real-World Applications and Next Steps.
I said it earlier, and I'll say it again. NumPy is a foundation. It is the absolute industry standard, acting as the literal bedrock that major libraries like Pandas for data manipulation, SciPy for scientific computing, Matplotlib for data visualization, and heavy-hitting machine learning frameworks like TensorFlow and scikit-learn are all built upon. By learning NumPy, you are quite literally learning the underlying language of all these advanced tools.
And because it powers all those tools, mastering NumPy unlocks the doors to some of the most cutting-edge technology on the planet. Whether you want to model complex markets and financial analysis, build the next generation of AI and deep learning algorithms, process images in computer vision, control the movements of robotics, or even optimize physics engines in game development, it all relies on fast, efficient numerical computation. It literally all relies on NumPy.
Congratulations! You now officially understand the fundamentals of NumPy, from creating dimensions all the way to performing vectorized math. You have built a rock-solid foundation today, but honestly, this is just the beginning. The natural next step is to take these raw numbers and apply them to complex, messy, real-world data structures. So I'm going to leave you with this final thought. You've mastered the numbers. Are you ready to conquer real-world datasets with Pandas? Keep practicing, and I really look forward to exploring that next step with you very soon. Thanks so much for joining me for this explainer.